You try to avoid this whenever at all possible. And so it's just one of those things. So this is going to be 1.0 times 10 to the minus 8 minus 7.05.
Yeah, that's why it's like negative 6.05.
Yeah, is that possible? No. So it's back to work, right? So on the test, if you're given something like this where the stepwise fails, then in order to get full credit, all you have to do is say, stepwise fails, it perturbs the previous step, must solve simultaneously, and then you'd get full credit. There are people who are really gung-ho and who will solve this, the algebra, and so you could do that for like bonus points if you want. So,
You want us to set it up?
if you set it up, you can get some additional bonus. If you solve it, then you get more. Okay. But setting it up is good too, just to see. All right, if you want, because this takes time to solve. I wasn't expecting anybody to have it figured out yet when I came back. So it takes time. So you can do this at home. We're not going to do it here. Okay. But what I want to talk about briefly are polyprotic acids. Next, we're just going to go for a little bit more, and then we'll stop. Like for example, a diprotic acid, A would be some generic anion. And so H2A. Well, H2A plus water gives us hydronium and HA minus. This would be called Ka for H2A, which is the same thing as what we call Ka1 for H2A. But this is a diprotic acid, so there's still one more proton here. And once we generate HA minus, then HA minuses can undergo collisions with water as well. And so HA minus can hydrolyze water in the second step of this to get some more hydronium and leave us with A2 minus. This would be Ka for HA minus, which is the same thing as Ka2 for H2A. So we have a diprotic acid here. If we have a triprotic acid, then we have this situation where we're going to have a Ka1, a Ka2, and a Ka3. Typically, what happens is the Ka1 is much larger than the Ka2, or larger, and the Ka2 is larger than the Ka3. So each subsequent steps, the acid strength weakens, as you'd expect. I mean, H2A would be a better acid than HA minus. And so let's take a look at the example here. We're going to do two pretty quick. We'll do 0.100 molar H2SO4. And so we have what equilibrium happening? We have Ka1, we have Ka2. It's for the two protons on H2SO4. And we have Kaw. And so we got to look at the sequence. Ka1 is it's a strong acid, so Ka1 is very large. Ka2 we look up in a book, and it's 0.011, and Kw is 1.0 times 10 to the minus 14. And so these would be the steps. As far as steps go, we have step 1, step 2, step 3. So step 1 would just be Ka1 H2SO4 plus H2O liquid. This is going to go to hydronium plus HSO4 minus. Since Ka is very large for this, the ice table is quick. If we start off with 0.100 molar, we're going to go down to 0 because all of it's going to hydrolyze. And that's going to leave us with 0.100 molar hydronium and 0.100 molar HSO4 minus. So when we have a strong acid, it's a one-way reaction. This one-way reaction can't be perturbed, by Le Chatelier's. So even if we increase the hydronium or we increase the bisulfate, the HSO4 minus, it's not going to impact things. But the hydronium doesn't stop there because we generate hydronium in the next step as well. And so this is Ka1. We go on to the next step, that is HSO4 minus, which we generate in the previous step, can hydrolyze water, H2O liquid. And so this is going to produce some more hydronium plus sulfate. And so this hydronium gets brought down to here, so our initial hydronium is 0.100 molar. But unlike in the previous problems, we have another species that's going to drop down. And the other species is the HSO4 minus. And so the HSO4 minus, initially, we're going to have 0.100 molar here. H2O is a pure liquid. And so sulfate, we're going to assume that none of the HSO4 minus has yet reacted. And so this will be minus X molar, plus X molar here, and plus X molar. And so at equilibrium, I'm going to have 0.100 minus X molar, 0.100 plus X molar, and X molar. Ka2 is 0.011, which is just going to be this Ka here. That's going to equal the hydronium ion concentration times the sulfate ion concentration divided by the HSO4 minus concentration. So this will give us 0.100 plus X times X over 0.100 minus X. Then let's just try the simplifying assumption. It might fail because not so small or not so big. And so the SA here is going to give us 0.100 on the top times X divided by 0.100 on the bottom. In other words, X is equal to 0.011. So if X is equal to 0.011, then that's 11 out of 100 parts. So it's an 11% change. This 11% change is too big. So the SA fails. That means we have to use the quadratic for this problem. So let's do that quickly here. So getting this into quadratic form, I'm going to multiply this binomial by 0.011. And so 0.1 times 0.011 gives us 0.0011. And then minus X times 0.011 gives us minus 0.011X. And then I'm going to multiply this X through here. So this is going to equal 0.100X plus X squared. And then I'm going to add this to both sides, 0.011, and then subtract this from both sides to get it into quadratic form. So this is going to be X squared plus 0.111X minus 0.011. And this is going to equal 0. So this is my quadratic. And then I'm just going to go to the quadratic solver. Unless, what did you get? 1 point?
9.19.
9.19?
15, sorry, 154.
154.
Times 10 to the negative
Times 10 to the negative
3.
3. Thanks. Okay, that sounds good. Turn this off. All right, we didn't use the simplifying assumption, so we don't have to justify anything. That should be the correct answer. And so let's go back over here and calculate the equilibrium concentrations. That is 0.100 minus Now I'm going to convert that into decimal form. And so this is going to be 0.100 minus 0.009154. And so I'll carry 3 extra zeros here. So this is going to give me 6, 4, 8, 0. 0.090846 molar. And then this is going to equal 0.100 plus that. So this is going to be, let's see if I can turn this off. There we go. Plus 0.009154. So I'm going to get 451,901. 0.109154 molar, and this will just be 0.009154 molar here. All right, next we should calculate K to make sure that these equilibrium concentrations satisfy the equilibrium constant expression. And so we'll take this 0.109154 times 0.009154. Divided by 0.090846. And I get a K. When I calculate my K for the check, I get 0.01099. It's supposed to be 0.00. No, here it is. Sorry, 0.011. Is that good? This is good. And so we're good. So far, here, is that going to perturb this step? Because we just added another 10% hydronium in step 2. And so far, step 1 generated 100. We add another, about 9% more, whatever, 10% more. Actually, more like 9% more. Will that perturb this step? So the hydronium increase, is that going to screw up this equilibrium? No, because this equilibrium is just a one-way equilibrium. So even if I put 0.109 here, it doesn't mess anything up. But we're not done yet. We have step 3. And what is step 3? KW. So we got to see, how much more hydronium we're going to get from water. So step 3 is going to be H2O liquid plus H2O liquid. This is going to give us hydronium plus hydroxide. And so initial here, hydronium is going to be from this step. So we got to drop this down here. And it's going to end up here, 0.109154. The hydroxide is going to be 0 molar because we're going to assume that water has not yet hydrolyzed or reacted. There's no water collisions yet. And then this would be the end of the line for HSO4 minus. This would be the end of the line for sulfate. This is not the end of the line for HSO4 minus. We don't want to double count here. Okay, so we're going to get plus X molar when this reacts, giving us 0.109154 plus X, times 10 to the, no, not times 10, just plus X molar and X molar. So plug those into the KW expression, 0.109154 plus X times X. Here I'm going to just try the simplifying assumption. This is going to be 0.109154 times X, and then that means X is equal to 1.0 times 10 to the minus 14. So 1 times 10 to the minus 14 divided by 0.109154 equals 9.16 times 10 to the minus 14, which gives us a percent change, which is x over the original. So I'll just leave this in the calculator divided by 0.109154 times 100. The percent change is 8.3 times 10 to the minus 11%. If you see a percent change that small, that means you're wasting your time doing the quadratic. You know, we wouldn't bother doing the quadratic here because we get just as good of an answer by using the simplifying assumption.
Isn't it negative 10 to negative 14?
This one?
No, never mind. You got it.
Okay, over here it is. So what that's going to do is this. Okay, hydronium is 0.109154. And how much additional hydronium are we getting from water autoionization? It's going to be, I'm going to write this in decimal form. And so it's going to be plus x. And so x is going to be point, and now I need 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then a 9, 1, 6. So let's add some zeros here. 3, 6, 7. So I'm going to get 0.109154, and then 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then a 9, 1, 6. And then the hydroxide. The hydroxide is 9.16 times 10 to the minus 14 molar. And so let's double check our K to make sure it's okay. And so I'm going to get 0.109. Can I put this many digits in my calculator? Have you ever tried to put that many digits? It doesn't work. So I'm just going to go 0.109154. That's in, times 9.16 times 10 to the negative 14. The K comes out to 9.99 times 10 to the minus 15, which is equal to 0.999 times 10 to the minus 14, which is good, because that's going to round to 1 times 10 to the minus 14, which is what it should be. But we don't stop here. With each step, we have to check to make sure it doesn't perturb the previous step by Le Chatelier's principle. And so does this step screw up the hydronium in this step? No, because we say that this is negligible. You know, the amount of additional hydronium we have here is negligible, and therefore these two concentrations are approximately the same. So we have the same hydronium ion concentration satisfying both equilibria in a stepwise fashion. You know, there is a slight change, right? So it's not perfect, but you know, the slight change is so small, it doesn't really register. And so fortunately, we don't have to solve this simultaneously. Okay? And then what we'll do is we'll just summarize our results. So basically, we're going to have a beaker. And this beaker is going to be labeled 0.100 molar H2SO4. And then we'll just inventory it. The H2SO4 molecule concentration should be 0. We don't expect any H2SO4 molecules to be unionized. And so this is going to be 0 molar. The next highest concentration will be hydronium. The hydronium ion concentration will be 0.1091 molar. And then the next highest concentration should be the sulfate, is that right? Yeah. The sulfate, no, not the sulfate, the HSO4 minus, yeah, HSO4 minus, at 0.0908 molar. That's this. So we have this. We have this. This gets carried down. These two got carried down. This stays. So this is not going to be in order. We're going to have sulfate at 0.0091 915 molar. Okay, and then the hydronium ends here, so this is the final hydronium that's going to satisfy all three equilibria, which we have here already. And then the hydroxide. The hydroxide is going to be the species in the lowest concentration. I mean, this is an acid. So this is going to be 9.16 times 10 to the minus 14. Okay, is that all the, yeah, I think that's all the species. And so the pH is going to be based on the total hydronium, right? And so the pH is equal to the negative log of 0.1091. So 0.1091, the log of that. And the pH is 0.962. That would be 3 sig figs. Now, you're going to get two types of calculations in Chem 1B. The first type of calculation is going to ask you for the inventory. If you have to do the inventory, we need to do all three steps. The second type of calculation is going to ask you for the pH. If we need to do the pH, did we really have to do all three steps? If the only answer they wanted was the pH. No, we could have skipped the third step.
But then you wouldn't know if it's negligible.
You wouldn't know if it's negligible, but we have plenty of clues that it's going to be negligible. The clues are the magnitude of the K values. The K for step 1 is very large. The K for step 2 is 0.011, which is still fairly large. The K for step 3 is 10 to the minus 14, which is many, many orders of magnitude smaller. And so initially you don't know, but pretty soon you'll get more and more clues as to when we can skip it. And so we'll talk about this more, but keep an eye on, you know, what's actually required. You know, the safe thing to do is do all three, but if you're pressed for time, then you want to skip it where it's possible to skip without, you know, sacrificing your answer. All right. So I'll stop here, and then we're going to continue with the lab.